Thanks everyone for joining today's Space Syntax Lab seminar. I'm really excited to welcome Dr. Stephen Law to talk about plausible counterfactuals to explain urban imagery models. Stephen will talk about a new method aimed at making urban imagery models understandable, particularly also to non-expert and more useful for planning processes. Stephen is a lecturer in social and geographic data science at the geography department here at UCL, where he also leads the MSc program in social and geographic data science. He's also a Turing Fellow at the Alan Turing Institute, the UK's National Data Science Institute. And Stephen's research is interested in space syntax, geographic data science, computer vision, spatial network science, urban economics, urban planning, and urban design. And he has over 10 years of international consultancy experience in urban planning as a consultant at Space Syntax Limited, and he has completed his PhD at the Space Syntax Lab on the value of spatial configuration. So we're really very much looking forward to hear Stephen's presentation. Before we start, as usual, if you have any questions during the presentation, please put them in the chat so we can address these during our Q&A session, which today will be hosted by Yishan Sun. She's currently undertaking a PhD at the Space Syntax Lab. And with this, I'd like to hand over to Stephen.
Thank you. Thank you, Kimon. Originally I wanted to give a talk for something closer to space syntax using street networks, but unfortunately the paper didn't get published in time. So instead today I wanted to present to the space syntax group and researchers on some recent research I did on the image analysis, which I think we can also which I think is also useful to think about from the context of urban analytics and evidence-based design. So today, the paper that I'm presenting is called Explaining Holistic Image Regressors, Classifiers in Urban Analytics with Plausible Counterfactuals. And this is joint work with Rikul, Brooks, Chris, and Andrew in various universities. And this was a paper that started during my postdoc maybe three years ago, and it was funded by a small fellow grant at the Turing. So this is the contents of my presentation today. I'll briefly give an overview and background and motivation of the work, some previous works in this setting, the method that I propose for this research, some regression results, qualitative results, and human evaluation results. I end with some discussion, future works, and some limitations of the method. So as everyone knows very well, that artificial intelligence has made impressive strides in the past 10 years for many domains. So for an example here on the left, a lot of these techniques are used for autonomous vehicles, for example, driving around where you need to detect whether there's a pedestrian crossing a road or not. And also in things like medical imaging to detecting cancer, or in video games of Go or StarCraft and so forth. And importantly, for us, it is increasingly being used in urban planning and design. And this paper on the right by Han here basically developed reinforcement learning agents to basically lay out different block configuration to see which one would maximizes a reward here, which in this case is some kind of environmental indicator. So in this slide, I just want to say that AI is making a big splash, including in our domain, urban planning and design. So a commonly used AI technique is image recognition or image analysis, which in urban analytics is used to retrieve information such as urban enclosure, some research I did at the Turing with another PhD students, street frontage quality, some research I did where I show here, I'll talk a bit about later, architectural ornateness or greenery. And these information can be very useful in planning, as it can identify areas that might need more active frontages, greenery, beauty, or an enclosure. So to give you an example here, this is a paper I did with Shen Yao and Shinuki in 2017 and 2020, where we basically developed in that time, it was kind of state-of-the-art, a CNN model to predict whether the image has active frontages or not. So it was like a 4-class classification, and then we got an accuracy of about 93% using both Street View and synthetic images that we created from City Engine. So the really cool part of this kind of model is it allows you to infer for the whole city, because if you train a model that has a very, very high accuracy, it means that you'll be quite confident that it'll work for a larger area. So when we kind of run this algorithm for like central London, as you can see in the left image here, it picks out like mostly its active frontages. And on the right here, you can see near the Isles of Dogs or Surrey Quays, or this is kind of old. So there's less buildings near the Millennium Dome, but a lot of these streets has inactive frontages. And a really nice, like I think a use of these kind of techniques in image analysis for urban planning and design, it can identify problematic areas and areas that might need maybe some kind of intervention. However, so to give a background on how these model works, most of these image models essentially learns a function that can classify an image into 2 or more classes. And these are the kind of models that kind of propelled AI about 10 years ago. However, a criticism of these techniques is that these functions are often black box in nature, which means that the parameters it learns are non-interpretable, meaning that you don't really know what the feature it is learning because it is done in a black box nature. It is done automatically. So to give you an example here, we have a natural image of a rock garden. We feed it through some black box model, and these models can tell you whether it is a rock garden or not rock garden, but you don't really know how it happens. And this is what we mean by the black box nature. So the question is, how reliable is it and how trustworthy is it when you're using, when you want to be responsible in using these algorithms? And we argue that explainability is critical in urban planning and design, as decision needs to be reliable and trustworthy. Therefore, this research paper contributes to developing methods on explaining these black box models in urban analytics. To give an example of some like research I'm recently doing, so consider an image here like a 3D view of Tokyo from a window of a property. You feed it through a black box model, and it tells you whether it has high window score or low window score. The question is, why is it making such a prediction? So for example, this view looks pretty nice. You can see Mount Fuji in the background, you can see Tokyo Tower, and most people will rate it highly. However, how do you know which parts of the images is doing that? And this is what I think is problematic of these image models. It doesn't tell you why or how. So this is some research that I did 2 years ago in the computer vision sphere, where we borrowed an explainability method here called counterfactual explanations, this kind of concept. We borrowed this concept that asks what would need to be different for another outcome to occur. So when we implement, when we kind of apply this concept into image space, what happens is we would want to change an image minimally towards the margin of the classifier, meaning that we want to change this image here, a butterfly image, towards the margin of not being a butterfly. And basically, this equation just minimizes that. And when you're wanting to change it minimally, what happened is you create this image on the right here called perturbed. So these two images are basically exactly the same. So they're often called adversarial perturbations. However, they are actually slightly different because they have been perturbed minimally towards the margin. And when you take the difference between these two, like perceptually similar looking images, you actually, when you take the difference, you get this saliency map. And these heat maps basically would tell you, gives you an explanation of this model that tells you that this image is a butterfly. So this is a really cool research because we basically applied this kind of adversarial perturbation to basically explain this kind of imagery model by identifying the objects in the actual image. And we got pretty good results when compared to other state-of-the-art methods like RADCAM. So this was 2 years ago, so there's probably a lot more new methods now, or RISE, or Excitate. Like there's a lot of different methods, and we perform competitively to all these other classifiers, all these kind of explanation methods. So as you can see here, like most explanation methods that are really popular nowadays are kind of using these kind of heat map methods. And what we notice with these kind of heat map methods is they're very, very good at picking out the objects. So for example, if your classifier is asking, does it have a dog? It picks out the dog very, very clearly. Or when you're applying to find a polar bear, it would identify the polar bear quite clearly, and a bit of the ice because they probably correlate. And when you have a classifier for the bird, it identifies the bird very clearly. So it's very, very good when you have foreground and background objects. However, in urban design, in urban analytics, this is a lot more ambiguous. It's not just about finding cats and dogs. You might want to use this kind of model to predict house price, to predict how well the view is, or how beautiful the view is. So when applying these heat map methods in urban analytics, the results are less clear, and it gives a very general explanation of the classifier. You don't really know exactly. It is highlighting a skyscraper or maybe the skyline, but you're not exactly sure what it is highlighting. So this is kind of a critique on these kind of heat map methods in image classification that are often used, and we're critiquing it in urban analytics. It's not always helpful. So there has been a lot of works recently, especially in the realms of generative models, like for example, variational autoencoders, generative adversarial network, or more recently stable diffusion, that there are very, very powerful methods to generate an image. So the kind of motivation of our method is like, why don't we, instead of like creating this kind of heat map that tells you which parts of the image is a cat's, is it possible to actually change the image to another class? And this is using these kind of generative models. So in the method that we propose in this research paper is called generative counterfactual explanations. So instead of like perturbing it minimally so that the image doesn't change, we want to perturb minimally in the latent space, minimally towards this kind of target. In this case, the target may be a tree classifier. So this explanation will basically tell you that, will basically tell you whether this model is working or not, if it actually creates an image with more of the target that you're interested in. So to give you an example, if given a street view image on the left here, we call original, we feed it through a classifier here that would tell you how many trees it has in the image. The explanation of this image from this method that we create would be this perturbed image on the right. So this explanation on the right here is a perturbed image, which basically explains the tree regressor. So if it presents to you more trees in the image, then we know that this method or this classifier is working. So it is a way of a way to kind of explain the model, and it gives an intuitive understanding of these explanations, which these kind of heat maps we believe, or we argue, is less intuitive for non-experts. So we kind of argue in this research that these generative explanation is more intuitive for non-experts than the kind of heat map ones. This is the architecture of the model. It is a little bit complicated, so I'll go through these in steps. Step one is a generative model. So the generative model we combined a VAE and a GAN together only because it produced better reconstruction. So basically the generative model here basically compresses the image into a latent space Z, and it reconstructs to Z bar. And we also have a discriminator behind it that tells you whether the image is real or fake. So it is a combination of a VAE and a GAN. The next step is we use this embedding space to predict different targets. So for example, we predicted rather the number of tree pixel it has in the image, the number of building pixel it has in the image, or the number of sky pixel it has in the image. As you can see on the right here, the model does pretty well. So the image to targets kind of rate, R square is like 72% for trees, 65% for buildings, or 81% for sky. And we're actually only running a linear model from the Z model, like a very, very simple model in M. We also trained a second model, what we called an image enhancement model, and this is just to enhance further. So we have another GAN, which we call S here, which just enhances it. You can use any GANs like you like, and basically this is just is kind of an optional step, but we wanted to make the image more realistic, so we tried to put another GAN after it. So in recent, more recent research, I'm trying to get rid of this stage because this is like too many models to just recreate the image. But in this paper, we did include the secondary step for image enhancement. And the last step is the kind of the generative counterfactual explanation step, which basically perturbs the image in the latent space. So that you can see here, we perturb Y to Y prime here, so that you have a new Z prime in the counterfactual explanation kind of loop. And then after you have this like new Z prime, this perturb latent space, and then you can create a new image here, X bar prime. And when you enhance it, you get this image on the right here, a more enhanced version of a tree, kind of an explanation of a tree model from the original model of X. So this is the results of the research. So we first have the regression results here. So we find that, of course, there's a strong fit between the image to the regression targets. However, we found that the results drop dramatically when we use the generated image and regression targets. So for example, if you use not the image itself to predict the kind of trees it has, if you use the generated image instead, what happened was like the regression drops dramatically to 0.078 and 0.462. And this means there's some kind of cycle inconsistency in the regression, meaning that the generated image does not really correspond as well to the kind of normal image space. And this is kind of expected because they're kind of different domains. So to kind of get around this, this kind of problem, what we did is we used the generated image, and we used the generated image to augment the original regression model. So rather than just feeding in the existing image, we actually included the generated images into the regression loop, because or else the regression would be really too low to be cyclically consistent. So this is one of the first findings we had, is we needed to include this additional generative augmentation loop to make sure that the regression results are consistent. So these are the results from the model. On the first column here are the 4 different street images. On the second column here is one for the tree regressor. So we try to increase the number of trees in the image. So you can see that they all did that. So it means that the tree model was kind of like consistent here. But you also notice some artifacts that I'll talk a bit about later in the end, that there's some slight realism problem here that it creates these kind of image artifacts on the image. But as an explanation method, we think it is fine. But if we use this as a generative tool, then we think it needs more improvements. And then this third column here, you have for buildings. So in this column here, we try to create we create an explanation for a building regressor. So of course, the more buildings, it means that it kind of is what is expected. The increasing in building density compared to the existing image. And lastly, here is a regressor for sky. So we're increasing the number of sky pixel in the street image, and it does increase the number of sky pixel. So we think the 3 models that we trained here are quite reliable because they are as what we would expect. The explanation is what we would expect it to be. So we did a bunch of hyperparameter tuning to make sure that to test these results. So what happened if you tune the trees very, very high? So what we notice is like when you tune it too high, is like the image becomes really broken up. So there was some kind of sweet spot that we had to tune kind of like manually from these kind of hyperparameter tuning. This is kind of common in this kind of domain. And we also did some comparison from nearest neighbor. So there's a question on like there's a paper that we quoted from Nokia Bell Labs, that rather than, because they also found that these generative images sometimes are not realistic enough, so they use a nearest neighbor approach. So we also did kind of like a baseline comparison to a nearest neighbor approach, and we think our kind of counterfactual is a more realistic one than the closest image in the kind of latent space. So in the last kind of experiment, to kind of validate this method, we kind of ran a human evaluation experiment. So very, very simply, we basically have this, we basically randomly choose an image, and we would perturb it for like different classifier. And so if we would then ask like, what is changing on these like 3 street, it's not 4, it's 3 street view image. You can put your answer in the chat box if you want to take a guess of these 3 images. I'll give like 10 seconds for you to put the results for these 3 images. What is changing on these 3 street view images, if you're interested. So basically, as we would expect, the things that changed were adding trees, adding buildings, and adding house price. And this was kind of the human evaluation experiments we asked. We asked basically what actually changed in the image, and we see whether the change corresponds with the explanation or with the classifier targets that we're like aiming after. And if the explanation targets corresponds with like what the answer of the human evaluator, then we click that as kind of a correct. So we did 4 basic experiments to that. So experiment 1 and 2 was basically asking people to select image pairs that correspond to those kind of changes. We also did one with the heat maps as a comparison. And then for experiment 3 and 4, we asked people to describe in natural languages what happened to the street images. Was it adding trees or adding sky? And similarly, we did the same with the heat maps, asking people which parts it highlights. And this is the results from the human evaluation experiments. So the accuracy here is measured by how many times but the participants gave the same response as the classifier targets. The higher accuracy, basically, the better is the model explanations. So you can see here the generative method did better than the heat map method. So for experiment 1 and 2, it has an improvement about 15%. And for the description experiment, it has an improvement about 9 to 10%. So you can see here, this generative explanation is not perfect. But it is for these. So for example, I forgot to mention the human evaluation experiments was done in Amazon Mechanical Turk, where we asked non-experts to rate these for these 4 experiments, and we try to aim for about 700 to 800 samples for each kind of experiments. So this was the results from that, and the standard errors in the brackets. So basically, the kind of conclusion from this slide is that for non-experts, the generative explanation seems to be a better explanation than the heat map ones by some statistically significant margin for all 4 experiments, or for these 2 pairs of experiments. So to go a little bit deeper, we have found that, how come the generative explanation is not always doing that well? It's actually only getting a 70% accuracy. How come it's not higher? And how come the heat map one is still quite high? So we went down into a little bit more detail. So we explicitly looked at experiment 3 and 4. So experiment 3 is a counterfactual one, the generative one, and experiment 4 is using the heat map methods. So in this experiment, we basically asked, describe in 1 to 4 words the change that happened to that, for example, street image. So we have 1 image, and then we have 4 images on the right that made these changes. So, and what was kind of surprising to us was that things like trees and buildings was very, very accurate with the generative models. But then the sky was actually very, very inaccurate with the generative models. While in opposites, for this heat map ones, the tree and the building one actually was much poorer in terms of accuracy. But in terms of sky, it is actually doing very well. So what we can say here is that these heat maps methods, even though they're less intuitive for non-experts, they might still be useful for picking out background elements like the sky. So for example, if you have an image of highlighting the sky, is a lot easier than creating more sky in the generative image. So kind of a conclusion from this kind of results is that the generative models are generally better to explain kind of urban objects that we have, like trees or buildings and so forth. However, that they're not necessarily better for more background objects. And in this case, heat maps methods are still better for explaining these kind of models. So as kind of a discussion, how can these methods be used in planning? So to summarize, we developed a counterfactual explanation method to explain these black box imagery models in urban planning and design. And we found that non-expert user intuitively grasp the generative counterfactual explanations better than the heat map explanations. But there are, of course, these exceptions I mentioned earlier. We argue that greater explainability increases the reliability and trust of these models. So we think that do spend the time to, if you're using these kind of methods, is really important to also see if they are doing what it is expected of it. And visualizing these counterfactuals can also be useful in engagement and communication. So this was kind of like a side kind of a outcome from the research. It's not just to explain, but you can also use this as an engagement and communication tool. For example, how does the street look like with more trees, or in space syntax term, higher spatial integration, or an extra cycling? So I didn't put the results here, but I actually did some experiments where I used these images to predict integration directly, and we got an R-squared about 0.43. So there are some relation. You can kind of guess how integrated an image is. And here's I made a small video, which I think could be really cool, using these generative video methods. You can, from these counterfactuals, you can actually generate some video that you can then use for engagement and communications, and it makes the kind of cases a lot easier than it can. So some future works. So one future work that I'm hoping to kind of engage in is like, rather than just, I don't know, explaining these machine learning models, can we put it into a pipeline for imagining how a city could look like? So for example, this is another paper that I recently published with some colleagues in UCL Geography and the Turing, where like we want to predict the number of trees, canopy quality for the city of Chicago. And then we relate it to like an urban heat island effects. And the aim is basically to plant like number of trees in Chicago using these kind of like machine learning methods. And with these kind of tools, then they would allow us to not just visualize, not just tell you how many, like where should you plant trees in Chicago to be more equitably sustainable, like to reduce the land surface temperature, but it can also, for example, visualize the outcomes. So for example, I'm interested to maybe create these environmental counterfactuals to actually show this is how it could look like in kind of this kind of like urban design pipeline. It's not just about where the trees are or how it could improve, where should you plant trees, but how it could also look like. So I think there's a lot of potential for these methods of not just explaining, but actually engaging with the public. It's a lot more intuitive, I think, than maps. So I want to briefly discuss about limited realism from these kind of methods that so the paper was done in like these past 2 years ago, so we didn't really use the state-of-the-art kind of generative image models. And I would say that one of the kind of criticism of the current work is like it's not as the realism is not as good as it could, and recently there's a lot of research in using much better generative models for this kind of task, like stable diffusion. So like one potential avenue to improve these models in the future is to use better kind of text to image or image to image models to improve the synthesis for more realistic counterfactuals of the urban street scenery.